It's hard to imagine anything so massive, so physical as a wheel loader. And in relation to that, it's easy to understand the benefits of using simulation in the product development process. And virtual simulation is actually starting to play a bigger and bigger role in the creation of these huge machines, to a point where it's a critical part of the product development process. And in places that previously relied largely on physical testing, the use of simulation software is becoming more and more prevalent. This also affects the approach to product development work. By studying phenomena at an early stage in the process, perhaps even in the concept phase, with things like 3D models, you not only lay the groundwork for creating better products and solutions, but also have a potential to cut lead times and costs, not only when it comes to the internal product development, but also how the products are used by the customer and how effective they are there. And one of the companies that are aggressively pushing the simulation angle is Volvo Construction Equipment. So we've talked to their specialist, Dr. Reno, to discuss the role of simulation in their operations. So Volvo Construction Equipment is the second largest segment in the Volvo Group. So exactly what are you designing and building here?
Well, we can start by looking around here. We have wheel loaders here, an excavator here, an articulated haulers. These are what we call the production machines. But we have a road segment as well. Pavers, graders, compactors, milling machines. So these are the two major segments, I would say, we have within Volvo Construction Equipment.
And when it comes to simulation, you have a lot of people working with these types of software. How many are there?
Well, I would say we have about, let's say, 50 people working in a department called virtual product development, different aspects of simulation. And I would say we have quite a lot of people around in departments designing machines that are using simulation as well, like 20 or 30 more. So I would say it's a critical mass.
Definitely a critical mass. So let's take a closer look on how simulation is used in the company. As we previously noted, virtual simulation seems to be growing in importance. Would you agree with this?
Absolutely. It's really important for us to be able to develop a bunch of concepts, pure in virtual reality, let them compete against each other, and take the winning concept and take that further into industrialization. And we wouldn't be able to do that physically. It's just impossible to develop several variants of a product physically as a prototype, test drive them in reality. I mean, it's just too expensive. But in virtual simulation, it's not only possible to do it that way, but we also can test like robustness and stuff that's really almost impossible to do in real life.
Would you say that there is a problem in this context when it comes to producing results that you really can trust?
It's really important that you don't have a perspective, you're just buying a software, you know where the buttons are, you press them in the right order, and then you're taking the result you're getting and think that's reality or that's the truth. You really need to have an engineering background, you need to have experience, and you need to utilize that. So it's really not just buying a software, go a course, and it's years of experience, and I think that's what pays off.
So in terms of physical versus virtual simulation here at the Volvo Construction Equipment, do you see a trend towards the virtual way of doing things?
Yes, absolutely. There's no denying that. I mean, it started 30 years ago with finite element methods, and that's fairly established, or firmly established actually, today. Today, is fuel simulation is very important and very interesting aspect. And the traditional way of doing that would have been building a physical prototype, going out in a working place and testing it in different scenarios. Nowadays we can do that in computer, so that's really, really great. And we are also able to vary some parameters, testing model in terms of robustness, and all that in a very early stage in development. Fantastic.
It has been discussed, especially on the automotive side, whether you dare to go to a model where you only have virtual prototypes. Do you think we'll get there?
That's a good question. I wouldn't say we will reach that goal maybe ever, but we're getting near it every day. But in the end, think about a car, and the driver has to have a certain feeling for the car, and that's a term it's very hard to quantify in a computer simulation. So I would say at least that aspect will always require a real human being testing a real car or a real machine. But everything else, we're really working hard at it to do that in the computer.
Now, you've done a study where simulation work has been used, and it is about the interaction between machine and operator for the wheel loader. We're going to look closer at this case, but we'll conclude by checking which software do you use in this case?
In that particular study, I used Adams to model the machine, a three-dimensional multi-body system. Hydraulics was modeled one-dimensionally in Adams Hydraulics. Drivetrain and all other stuff in Simulink. And a special case was the operator. Whenever I interviewed professional operators, they talk to me in terms of rules of thumbs or simple rules. Do like this when that happens, otherwise do like this. And to me that sounded like a perfect case for a state machine, so it was Simulink State Floor I used. And it was a co-simulation of all three parts, and that was a bit tricky to set up. Took some time to simulate as well, but I'm pleased with the results.
So we have moved to an excavator simulator, and Dr. Fella, simulation can be used not only for product development, but many other processes as education, as training.
Oh, absolutely. I mean, these are training simulators we sell to customers, large customers who want to educate the operators to drive or operate more fuel efficient, but also with a focus on safety. So you can imagine in a simulator you can actually train situations that would be dangerous to test, like tipping over machines or testing in reality. You don't want to do that, so it's perfect to do that in a simulator.
So without compromising the safety of the driver, you can train situations that are really loaded with mental stress.
Oh yeah, absolutely, and that's one of the advantages I see, because you don't want to endanger a driver or anyone around. And these situations are quite frequent actually. When you think of an operator like here on an excavator, you have a production quota to fulfill. You have to move a certain amount of material in a given time. So you're really focused on that work. And it could be, if you're not educated enough, that you're compromising with safety. You're not looking out anymore. You're not looking on bystanders. Yeah, it could be that you're not paying enough attention to how stable you actually have positioned the machine. So looks perfectly stable, you swing around and suddenly you tip over. So that's, these are things you can actually try to assess in a simulator.
So we're standing in the bucket of a wheel loader, and this is exactly the type of machine you have studied. So give us some numbers.
That's correct. That's the L350F. That's our largest wheel loader model size. And the bucket here is 6.8 cubic meters. So the machine 350F is about 16, 17 ton size or load you can take. It's quite a lot.
Now imagine to do simulation, physical simulation with a huge machine like this. It seems to be a little bit easier to use software.
Yeah, absolutely, and especially when you think of the cost. Having one prototype and maybe even driving it to pieces. That's a lot of development cost you're saving with virtual development.
When you fill the bucket, there's a lot of forces involved, and material and particles and things like that. Can you simulate that actually?
That's a real challenge today, actually, because it's there are different types of materials, like gravel, that's more or less small particles, but if you think of soil or clay or so, there are a lot of different material properties that we have no idea how to model. For instance, the moisture in the clay or in the soil really plays an important role. And typical simulation times, I would say, for like a 10-second of bucket filling sequence, 5 to 8 hours on a very good computer. So it's nothing you really do in a real-time simulation or trial and error. But once you get through this and you actually do that, you have fantastic analysis you can do, and optimization, for instance, of bucket geometry. Because a lot of fuel efficiency of a wheel loader cycle actually depends on things like tire, the bucket geometry. So that would really enable us to optimize the bucket.
So now we're on the inside of a wheel loader, and this is what you've studied, the role of the driver and the interaction with the machine. So what did you find?
Well, As an engineer, of course, you always want to measure stuff, quantify it somehow, and yeah, finally also able to simulate it. One hypothesis was, all right, things like heartbeat, respiration rate, how fast you breathe, how sweaty your hand palms are, and all that, finger temperature, is somehow a measure of stress, how stressed you are. And the question was, okay, is that stress also somehow correlated to how well you feel the machine interacts with yourself? Try to do that. And the other one was, if you're really driving and operating, everything works smoothly, you don't have to readjust how you use the levers and how you press the pedal. You just do it and it's right. But if you have to readjust quite a lot, then the idea was, all right, that would mean that the machine somehow isn't really reacting like you want it to do. So these were the two ideas, measuring a lot of things on the physical body of a human being and looking how the human being actually is using machine controls, and then look further, okay, does that correlate to how well the driver thought the machine was balanced?
So we're talking about the aspect of mental stress here, and that also means a lot for the performance and efficiency of the driver doing his work.
Exactly. I mean, you're not only working, you're also supposed to look out to drive safely, but on top of that, you're carrying a lot of baggage with you. Maybe things of personal nature stressing you out, and all that eats away on the sort of capacity you have to handle things. And what we need to make sure is that there's capacity left. And what we found is that if the machine is really hard to operate and you add all that personal stress, then the operator hasn't got the mental capacity left to also drive fuel efficiently.
Now, this simulation aims to build a number of improvements, and you talked about smart machine. What does that mean?
To me, a smart machine is a bit like a horse. And then you think, of course, a horse, is that smart and is that even a machine? Well, let's take it this way. There's a well-defined interface between the driver, which is the rider, and the machine, which is the horse. And the rider isn't actually commanding all the legs of the horse and how they're supposed to move. The operator or rider really just points into direction and selects speed. And the horse is actually moving the feet semi-autonomously and trying to avoid obstacles, going around or jumping over. So there's a lot of inbuilt intelligence in the horse. And I would like the machine to behave like a horse, so that you're, in the end, maybe you're just pointing on a gravel pile and sort of commanding the wheel loader to, okay, take the gravel here, put it there onto a truck. And the machine is doing that. And you're just riding along as a rider or as a supervisor.